All right, so today we're going to do Unit 5, Lesson 2, Patterns of Growth. So we're going to compare different patterns of growth. Here's a table. Which one doesn't belong? All right, so table A is the only table that doesn't start at 0, 0, or any value on the y-axis. You cannot see a y-intercept. If you look at the pattern, the difference between 8 and 16, it's increasing by 8. 16 to 24, it's increasing by 8. So we're just adding 8 every time. Okay. If you look at table B is the only table that shows only even values. You can see 0, 2, 4, 6, 8. All the other tables have a 3, so it has odd values. And it is increasing by 16 each time. Okay. Table C is different because it shows a nonlinear growth. Table A and B are both linear because they're increasing by the same amount every time, and it doesn't change. So it's constant, and that makes them linear. Table C, if you look at it, it's increasing by a factor. So to get from 1 to 4 and 4 to 16 by doing the same thing, you have to multiply by 4. So instead of adding, we're multiplying. So when you do that each time, it changes the factor, not just by the same amount every time. So that makes it nonlinear. Table D, it's the only table that shows linear growth by 4. So this one is a factor of 4. This one is increasing by 4. So we're adding 4 every time. Okay, and it also doesn't have 64 as a y value. So table A, we have 864, table B is 864, and table C is 364, but there is no 64 in the y value for table D. So let's look at this problem. We have another table that I want you to look at the pattern and see what you notice and what you wonder. All right, things that you might notice is that the number of stores nearly doubled between 87 and 88. The number continued to grow, and it wasn't doubling anymore, but it was a little more than 1.5 times from most years except for between 90 and 92. They added close to 1,000 stores in 10 years. You might have wondered how many stores they might have in 2015. That spot was left blank, and if we continued that trend of 1.5 times each year, we would have ended up with about 22,519. And then 24,000 in 2017. You might have wondered how the stores increased by roughly the same number since 1996, if we can't see that trend, okay? Or how was this company able to add so many stores throughout the year? So those are all things that you could have noticed or wondered there. So next we're gonna look at an example and look at 2 different plans. Okay, so we have a food company that currently has 5 convenience stores. It's considering 2 plans for expansion. So plan A is to open 20 new stores each year. So we're going to complete this table. So if we start out with 5 stores, and so that's our initial amount. If we're going to add 20 stores every year, then I'm just going to add 20 to that. So 5 plus 20 is 25. If I continue that trend and continue adding 20 each year, we're going to end up with 205 stores in 10 years. So the difference from each year is 20. So from 25 to 45 is 20, 45 to 60, and so forth, all the way down until we get to 10 years, the difference is 20 because it's constant. So this is a linear function. If we have n number of stores, how many stores will there be a year later? If n represents the number of stores I'm starting with, and I want to know the next year, I'm simply going to add 20. So n plus 20 will give me an expression to find the next year's number of stores. If I want to add, if I want to find out how many stores I'm going to have 3 years later, well, I need to get from 5 to 3 years later. So 1 year, 2 years, 3 years. So I need to get to 65. How many times did I add 20? Well, 1, 2, 3. So if I'm adding 20 3 times, that's 20, 40, 60. So my expression would then just be n plus 60. All right, plan B is to double the amount of stores every year. So if we start with 5 stores and we're going to double it, the next year we'll have 10, and then we're going to double that. So we'll have 20 and continue to double the stores every year until we end up with 5,120. So now the difference isn't the same every year. The difference from the initial year till the first year was 5, and then it increased by 10, and then 20, and then 40, 80, 160. So it's doubling essentially. So we're taking these values, instead of adding every time, now we're multiplying it by 2. So if we have n number of stores one year, how many stores will there be a year later? Well, we're essentially multiplying it by 2. So just 2n, or 2 times the number of stores that we have. If there are n number of stores one year, how many will we have 3 years later? Well, we need to get from 5 and look at 3 years later. So we multiply it by 2 once, and then we're going to multiply it by 2 again, and then one more time to get to that 3rd year. So essentially we have 2 times 2 times 2, which is 8. So we just need to multiply n by 8. Or 2 times 2 times 2 is also 2 to the power of 3, which will give us that 3rd year after our initial year. So this function is no longer linear because we're multiplying by a factor instead of just adding the same amount every year. All right, so let's look at another situation. We're going to look at 2 situations. So a person has 80 followers on social media. So that's how many they start out with. And then it's going to triple every year. So how many followers will she have after 4 years? So that's what we're trying to figure out, is how many followers this person will have after 4 years. Situation 2 has an 80-gallon tank of water. So it also starts out with 80. And then it's getting filled at a rate of 3 gallons per minute. So how many gallons of water will be in the tank after 4 minutes? So our numbers are the same. 80, tripling, or 3, and 4, 80, 3, and 4. But the situations are different. So we need to look at what each expression and table will look like. So for situation 1, we have 80, so the amount of followers on social media, and then it's tripling every year. So we're multiplying by 3, and we're looking for 4 years. So we're going to multiply 3 4 times, and that will give us the amount of followers that they have. The table for this one, you can tell it starts at 80. That's the initial amount that we have right here. And then to get to the next year, it's multiplying by 3 to get to 40, and then multiplying by 3 again to get to 720, all the way until year 4. The third expression for this one would be 80 times 81. So they got the 81 because 3 to the power of 4, or 3 times 3 times 3 times 3, is 81. So this function is nonlinear because it is increasing by a factor, not the same rate. It's not the same number every time. Situation 2, we have 80, and we're adding 3 gallons every minute, and we're looking for 4 minutes. So it's 80 plus 3 plus 3 plus 3 plus 3. Our table, and then adding 3 4 times is the same as multiplying it by 4. So 80 plus 4 times 3 is also equivalent. Our table here, you can see that it starts out at 80, and then it's not multiplying, but it's adding 3 each time. So adding 3 every time for 4 minutes so that we can see how much water will be in the tank after 4 minutes. So situation 1 is nonlinear. It's increasing by a factor. Situation 2 is linear, and it's increasing at a constant rate of 3.
Princess